if you turned it in, you've gotten back your 1-1 and 1-2 assignments. 1-3 has been assigned, and maybe you've taken a look at it. Perhaps you haven't done any of it yet, but we need to answer some questions about it too, if you wish. So, looking at the homework, who has a homework question? Tell us which paper it is and which number it is. And let's get a fresh marker here. Let's go. Who's got something that I marked or scribbled out or something? Drew?
I just have a question for the 1.2, the instantaneous rate of change. Can we go over how to exactly find that? Because I got 20, but I just looked at a number between what I got.
That's what you do. That's what you do. Now, I can tell you how, I'm not going to tell you how you actually find it because that's using calculus, but what we are doing is exactly what you did. We looked at increasingly small intervals. We looked at a 0.001 interval less than 1, right? Look, 1. And a 0.000 interval bigger than 1. And so we split the difference, basically. That's what we did, yes. That's exactly right. Now, some of you are not calculating the rates of change correctly. The average rate of change is simply the slope. And how do we find slope?
1, 2 minus 1.
Exactly. So, if you want the average rate of change, you're going to figure out your y's, figure out your x's, and that's it, right? So, I'm just going to do this C, 0.999 to 1. And I realize some of you got this right. Julia, I got other pencil sharpeners all around the room. I don't know, does that one work? Yeah. Oh, good, okay. All right, so our function is this. If we write this out mathematically, remember we need our y's, right? Our y's to find the average rate of change. Let's find the y's. You plug in the x's. So h of 1 is going to be the y value when t is 1, when x is 1, minus h of 0.999. So here's my second y value, my first y value, and then I'm going to subtract my x's. So that's the setup for average rate of change. The function values are the y's. You need to find the y's. How do you find the y's? You plug in the x's. Okay? So, you can do this. Put 1 in, put 0.99 in, 999, and subtract 1. And I got, when I did that, I got 42 minus 41.97994 over 0.001. And then when I figured out what that was decimally, I got 20.016. And what's the unit on that? Average rates of change have units. The rates of change, like miles per hour, only this one is, oh, I guess I didn't tell you, but you know what that formula is. That formula is feet per second. That's how you do average rate of change. Y minus y over x minus x. And where do the y's come from? Plugging in the x's. Okay? Now, some of you, I don't even know what you were doing. You may have been doing it right, but somehow you rounded this off and got 20. We're not rounding off to the, our rounds are going to be to the 1,000, guys, always. A rounding is going to be to the 1,000. And we're not going to do intermediate rounding if we can help it. Okay. All right, we good on that? All right, what else? What other question do you have from some homework? Oscar?
On the 1-1, can you do number 2, please?
It's just a matter of plotting some points. So you have got the table of values. So you're just gonna plot the point -4, 3. Yours is gonna look better than mine. -1, 4, 0, 4, 2, -2, 3, 1, and 4, 2. And we're gonna stop right there. Now, some of you connected those dots. Can anybody tell me why that probably wasn't a good idea? It doesn't have, I mean, what you are graphing is the table that you've been given, and what have you been given? Some points? Did they tell you what to do if x is 1/2? Do you know what to do if x is 1/2? You have no idea, they didn't give you that value. So you graphed the values they gave you, that's it. Good? Yep. All right, who else? Who else? Yep. Oh, stop, so 1 second, I'm sorry, right? If they give you a function rule, like something like this, then can you connect the dots? Yes, because then you have a rule to find all those other y values. Okay, good, sorry.
1.1, negative number 4.
So why don't you come up and draw what you drew, and we'll see if, no, go ahead, just draw it. Bring your paper up and just draw what you drew, and we'll see if you can figure out. It could be right, and I'm gonna get it wrong. That can always happen. So is that exactly what you drew?
Yeah.
Now give us some x values. On you need to label some x values. We have no y's, so you don't need to label the y-axis, but you need to label your x. Remember, when they give you those intervals, like they did in the directions, increasing on -2, 1, those are x values. So from -2 to 1, it's increasing. So let's take a look at this and see if we can help her sort out what's going on. So it looks like our intervals, we got -2, we have 1, we have 4, we have 7, we have -4, okay. So those are the x, we didn't space them out very nicely, but those are the key x values. Okay, so we're increasing from -2 to 1. Well, is that true? Are we increasing from -2 to 1? Yeah. And then from 4 to 7, are we increasing? Yeah, that looks like we are, okay. We're decreasing from -4 to -2, and we're decreasing from 1. There was a little bit of a problem there. Because we're supposed to be decreasing from 1 to 4, and you kind of started back up, so, okay, maybe just smooth it out a little bit like that. It's concave up on -4 to -1, so -4 to negative, yeah, a little bit of an issue there because concave up means you're a cup, and what's happening here at 1, Riley? What am I doing here at 1? This is actually concave down, isn't it? And I'm supposed to be concave up all the way from -4, to -1, I'm sorry. -4 to -1. I can live with that, okay, yeah, that looks all right. And then 2 to 7, I'm just concave up, from 2 to 7, that looks good. And concave down on -1 to 2. Yeah, I think my only issue must have been right in here with that, because the rest of it looks pretty good. All right, anybody else?
On the 1.2, we do the instantaneous rate of change.
Well, I can't do that one without doing the ones above it. So I did, just already, I did the, interval I did this interval. And I got 20.016. And then I did this interval on my paper here. And I got 19.984. So and then there were a couple others before that. The intervals, I'm honing in on one and getting closer to one with all my intervals. So the instantaneous change at 1, now think about this. Here's 1. At 0.999, which is right here, I was a little bit more than 20. And at 1.001, which is right here, I was a little bit less than 20. Right? So at 1, where do you think I was? At 20, yeah. And if you look, it really is almost perfect in this example, because isn't this 0.016 bigger than 1? Or bigger than 20? And this is 0.016 less than 20? Yeah. So the way we're doing this is we are examining increasingly small intervals so that we can find the velocity at that 1, or the instantaneous rate of change at that 1 point.
Number 3 on 1.1, just C and D.
3 on 1.1,
And C and D.
C and D. Okay, all right, just talk about those. This was C, which I did earlier. And E is the instantaneous rate. Am I on 1 point? Oh, that's 1.2. Okay, I'm sorry, that's 1.2. 1.1. C says, where is that thing concave down? Well, where does it look like it's concave down?
Is it 5 to 7?
Actually, it would be 5 to 8. I actually said 4.5, but I can live with 5 to 8. All the way to the end, it's concave down, isn't it? Yeah. And what's the other one?
And then E.
E, increasing and concave down. That would be just from, I said 4.5 to 6, you might have said 5 to 6, because it's the only part of the concave down interval that's increasing, the rest of it's decreasing. All right, anybody else? Kennedy?
3B for 1.1.
1.13, which one?
B.
D. We're increasing and concave up. So look at your picture. Okay, so concave up means you're like a bowl, okay? So, and you gotta be increasing. So it looks like from 3 to 1 maybe? Excuse me, -3 to -1. We're going up and we're concave up. And then I maybe, oh geez, I'm so old. Looks like maybe 3 to, I said 4.5, you could say 5, 3 to 5. We're concave up.
I'll put that in, you guys mark it off.
Huh?
I'll put that in, you mark it off.
Okay, sorry, it's okay, sorry. All right? All right, what else?
1.2, number 1, C.
Child, find the average rate of change as a child as he gets older. How do we find an average rate of change? Right here. So he ends up at 44 pounds. He started out at 23 pounds, so there's my change in Y. And he started out, he ended up at 42 months, and he started at 18 months, so there's my change in X. And this is going to be pounds per month, is it pounds or kilograms? Yeah, pounds per month. So, I don't know, what is that? 21 over 24, which reduces to 7/8 pounds. All right, anything else from homework? Good? All right, and I need you to look at that thing that was stapled, the review 1113 that's stapled to the 11 notes. And we're not gonna do this whole thing, there are a couple problems that I think we ought to look at. And one of them is A, problem A. I've been letting you guys do a lot of group work, but I think some of you are missing some pretty important concepts. So you wanna really focus in. All right, we're on that review, 1-1 to 1-3 that I had stapled to the chapter 1 notes. And problem A says, here's the picture, what's f of 4? F of 4 is 2. Guys, f of is a y value, right? So I'm trying to find the y value when x is 4, 2, easy. Find all the values of x for which f of x is 4. All the values of x for which f of x is 4. How many are there? 3. 2 of them I can pretty much see right away. Did you say -1 and 1? The other one we're gonna have to approximate, so what did you say? -5.5, maybe 5.6, I don't know, something like that, right? Got that? All right, back side of that paper, let's look at C. We got a 24-hour period, temperature of a town, X hours after midnight. At what time approximately does the high temperature of the day occur, and what is the high temperature of the day? So what are we saying, between, yes, sometime around 3 o'clock, a little bit before 3 o'clock in the afternoon? And what is the high temperature? 76, 77, something like that, right? We're approximating, it's okay. Identify a time interval at which the temperature is increasing at a decreasing rate. What am I looking for? If it's increasing, it means it's going up, right? A decreasing rate means it's concave down. So where are you increasing and concave down? Can you find a time of day, approximately, when that happens? We're
4:15.
We're concave down and increasing. Concave down and increasing. So I'm saying, I'm thinking somewhere, but it starts somewhere between 9 and 12. And it ends right around 3 o'clock. Would you agree with that? Because we gotta be increasing and concave down. At approximately which times in the day is the temperature 40? About 3 and 6 a.m. E, another picture. At which of the points is the rate of change negative? So now you're not looking at an interval, you're looking at just a point, one of those key points, A, B, C, D, E, or F. At which of the points is the rate of change negative? What are you looking for if the rate of change is negative? Decreasing? Doesn't that mean negative slope? So I think there's only one point where that's happening. D. Yeah, D is the only point where the slope is negative. I mean, the slope's negative a lot of places, but that's the only point that's labeled. At which of the points does G have the greatest rate of change? What are you looking for? Greatest rate of change happens where? At a point of inflection. And what is a point of inflection? So you guys need to pay attention to these quick notes we do. What is a point of inflection? Where the concavity changes from being concave up to being concave down. When you, it's very hard to describe, but you can feel it when you draw it. So you're going from concave down, and then your arm twists and you go from concave up. That's a point of inflection. We're changing from concave down to concave up, or vice versa, concave up to concave down. So where does that happen here? I would say probably, what do you think? Not A. A is not a point of inflection. What's A? A is a minimum. Yeah, that's a minimum. The rate of change at A is 0. That guy has stopped moving for just a second and then he starts back up. All right, where is your point of inflection? I would say it's point C. Aren't we changing from concave up to concave down at point C? I think you could also make a case for B. B could also be a point of inflection, changing from concave up to concave down. At which point does G have a rate of change of 0? I already told you that is point A.
And if that maximum,
Maximum or minimum, think about throwing the ball into the air. From just that instant, it stops and then it goes down, yes. So your maximum rate of change happens at a point of inflection. The minimum rate of change, in terms of like 0, no change at all, happens at a max or a minimum. Last one is H. We'll look at H. An ant crawls along the branch of a tree. Okay. Here's its equation. Where T is in seconds, and X of T is measured in inches from the trunk of the tree. H. Problem A. How far from the trunk is the ant initially? Five inches. How do we know? If it's initially, guys, what's the time? 0. We have no time passed. It's initially. The initial value is always the y-intercept. It's always x is 0. So that's 5 inches. At which times is the ant at the trunk of the tree? Okay, what are we going to do there? Remember what your equation stands for. This right here is the distance from the trunk. If the ant is at the trunk, then what's that? 0. So it looks like he's there twice. He must be going back and forth. When is he there? At t equals 1 second or 5 seconds. All right, get out your circuit training paper. Again, we're not going to do all of these. There's some redundancy in them, so I don't want to do them all. But I want to do with your partner. I want you right now to do the first, I'm on the front page. Do the first and the third problem. Do the first and the third problem with your partner, and let's compare answers. The first and the third problem. Now, everybody should be done with these problems. Listen, they're linear. They're linear. What do we know about the rate of change of a linear function? Constant. So does it matter what interval I'm going over? No. So look at the first one. What is the slope of that first equation? 3. So what's the average rate of change for that linear function? 3. Now, in a minute, I'm going to do the work and prove that to you, but this is the kind of stuff you need to get ingrained in your brain. Linear functions have constant rates of change. So as soon as they say the word linear, you're done. You're on the slope and you're done. So look at B, the third problem down, other one I asked you to do. They tell you it's linear. So all you have to do is find the slope, don't you? So I did, and there it is. Now, I want to prove this thing. I'm going to do number 1. I cleaned up the function, so this is what my function looks like in number 1. To find the average rate of change on the interval from -2 to 0, I'm going to do g of 0 minus g of -2, and divide that by 0 minus -2. That would be the formal way of doing the problem. I already know this is the answer, but I'm going to do this. What's g of 0? -8. What's g of -2? -14 over 2. So what's -8 minus -14? 6. And 6 over 2 is 3. So if you worked all this out, it would still be correct. This is the work that you would do, but that's not necessary because the function is linear. Right? Linear. Okay. Question, the fourth question on this front page. The fourth question. I don't want you to actually do the problem. We can do that in a minute. But what I want you to do is prove that that's quadratic. they tell you it is, but how do we prove that it's quadratic? Actually, I like to look like this. So you've got this table of values, 0, 2, 4, 6, and 8. How do you prove that that's quadratic? Xander?
You have to find the slopes of like each like pair of two, and then just make sure that they go up by the same amount each time.
Exactly, so let's do that, okay? So we're gonna find the rate of change here, Xander, so what's the first one gonna be? -3 minus -3 over 2 minus 0, that's just 0? Alright, next two. 5 minus -3 over 4 minus 2, that is 4, 8 over 2. 21 minus 5 over 6 minus 4. We're doing y minus y, x minus x, rate of change. That's 16 over 2, that's 8. And 45 minus 21 over 8 minus 6 is, have we done what Xander said? Yes. If this had been linear, then all of these numbers would be the same, constant. When they go up or down by a constant amount, okay, that's key. Going up or down is not enough. It has to be going up or down by the same amount, which this one is, right? Perfect. All right, see if you can do, turn it over, the back side of that first page. The first problem. Back side of the front page, see if you can figure that one out. It's a little bit different, worded a little bit differently. See if you can figure it out. Brains going? Are they thinking at all? Are they thinking of anything to try here? What's your thought? This is H right here. All right, what are your thoughts? What do you want?
I just got -4 for the x.
Okay, so that's what we want to do, Oscar, that's exactly what we want to do. The problem is, how do we find h of -4? If -4 were in our chart, these are the h values, we'd be all set. Okay, so can we, let's forget the case study for a minute. Can we write a rule for this? Yes, because they tell us it is linear. And if it's linear, then we know we've got a constant slope, right? And don't we have a y-intercept? So let's go ahead and find our slope. What did you get? -15 minus 10 over 10 minus 0. -25 over 10. Did you get -2.5? So the equation of h is -2.5x plus 10. So the problem says we're going to find k of -4 So that's gonna be -4 squared plus 3 times h of -4. But now, can we find h of -4? Yep. So what is h of -4 gonna be? 20? 20? So 16 plus 3 times 20, that's 20. Did you get, 76?
But I think it's 20 years.
So we wrote this rule right here for h. This is our h function. So I need h of -4, so I put -4 in. -2.5 times -4 is 10. And 10 plus 10 is,
So you put the -4 in instead of like I thought you might distribute the thing, so you put the -4.
this is like a y. Think of that as a y. See, there's nothing to distribute.
Okay.
It's just 3 times y. So I found my y value. All right, we good on that one? All right, do the, in the lower right-hand corner, on that same page, lower right-hand corner, the relationship between x and y represents a function. Explain why it's not linear, explain why it's not quadratic, and then find the ratio of e to a. I think you can do this, but it's kind of one of the main points. So what are you doing? Are you doing something? Are you finding the rates of change? All right, and what do they turn it out to be? Not all the same, that's for sure. Not linear? Absolutely not. Not quadratic? Because are these two dropping, I mean, is there a pattern there? Are they changing by the same amount? Not by adding or subtracting the same amount, are they? So not quadratic or linear. Can you find the ratio of these last two numbers down here, B to A? B to A, can you find that ratio? Oh, not those two. This is 4 and 5. This is 8. Any idea about that ratio? Patrick?
It's 8/3/4.
Well, you want the ratio of B to A, so what would that fraction equal? Well, okay, we can figure it out your way. So you said, okay, A is gonna be 3/4, so what's B gonna be? 3/16. So then your ratio is gonna be 3/16 to 3/4, which is 3/16 times 4/3, which is 1/4. And is that what ratio these numbers are in here? 9/36, 36/144. So that was absolutely fine, Patrick. I shouldn't have shot that down, that's absolutely fine. You could have just used these output numbers that you already have, but that was fine. That was fine. All right, anybody have a question about that? A couple more to get down on this page, and then you're gonna have a little homework to do to study. Alright, we good on that? Okay, let's look on the next page of the paper. The second one in the first column. I should have numbered this. The second one in the first column. Okay? For the function pictured, which is greater? The instantaneous rate of change at point A, or the average rate of change from A to B? So look at the picture. Here's A, here's B. So which is greater? Here's the average rate of change, guys. Isn't the average rate of change the slope between those 2 points? The instantaneous rate of change is the slope of that, just at that point right there. The slope of the curve at that point right there. Which is greater? The instantaneous rate of change is greater. There's no math there. You're just looking at the picture and thinking about the tangent lines. The one right under that. The function is decreasing and concave up. Decreasing and concave up from negative infinity to something. What is the something? I heard a 0. Is it 0? Be careful, the function has to be decreasing. Is it decreasing all the way to 0? Negative 3? Negative 3. We're decreasing and concave up. I've heard a few like that on there. Several of that vocabulary is on your quiz. We gotta make sure we understand. Decreasing means going down. Concave up means making a negative. Alright? The middle one in the other column. The middle one in the other column, the other picture. Determine the average rate of change of the function from -1, x equals -1 to x equals 3. Think about it like this. X is -1, x is 3. If you're gonna find the average rate of change, don't you need to know these two values right here? So let's look at our picture. -1 has what y value? Let's see, -1 has, looks like -5, isn't it? And 3 has what y value? 1, 2, 3. 9? Kids, my eyes don't work right, these lights are very. Is it 9? So the average rate of change is 9 minus -5 over 3 minus -1. 7/2. All right, one right under that. Did you get linear? Okay. I did the rates of change, I think I did them right, I got 3 halves all on. How are we gonna go about finding A and B? ideas anywhere? Oscar? You're always good for an idea, I love you, Oscar. Okay, go ahead, throw it out.
7 times 3 over 2, and 8 times 3 over 2, and then you subtract, or actually minus a.
So this number right here
Yeah, so
is going to be 7 times 3 halves?
Yep.
So 21 halves?
Yep.
And this one is gonna be 8 times 3 halves, which is 12? Is 4 times 3 halves 1? I think we need to use the 3 halves, definitely. I'm not sure that, when you do something like that, Oscar, you wanna double check and make sure that it works for all your boys, and it doesn't. So, okay, all right, who's got a different idea? The 3 halves is gonna be valuable, I think. Luke?
I just cross multiply.
So you know, so tell me what you set up.
So I did a minus 4 over 7 minus 6 equals 3.
So, you said what now?
A minus 4.
A over 4,
A minus 4
A minus 4,
over 7 minus 6 equals 3 halves.
now, would that be true? What is the rate of change right here? Isn't the rate of change right here, A minus 4 over 7 minus 6? So would that have to equal 3 halves?
No, it has to be half of 3 halves because they're going by 2.
Okay, now, in a line, it doesn't matter, okay? Because lines stay constant. So Kennedy, very good that you picked up on the fact these are not equal intervals, and that's usually bad news. But with a line, you can get away with it, since it is a line. So A minus, so no matter what your pair of points, the slope is going to be the same. So yeah, that's interesting. So A minus 4 over 1 equals 3 halves. So 2A minus A equals 3. So did you get 11 halves?
Yeah.
Okay. And then you did the same thing for this one and got what?
I got 25 over 2.
25 halves? Okay. Did anybody have, now those are A and B values, so that's A and B, those aren't rates of change. Anybody have a different idea? Yeah.
I think formulas would be fx would equal 3 halves x minus 5.
Perfect, so you could write a rule, you know it's linear, you know the slope, and you have the y-intercept, right? So now you can just plug in 7 and plug in 8 and get those two values. So either one of those ways is fine, just great. Anybody have a question about that? Okay, quickly, I want to do one more. On the last page, the first one up here in the left-hand corner. Describe this behavior. Which of those statements describes this behavior? Why, Patrick? You're correct. Why? Say it loud so they can hear. Yeah.
Well, it's increasing, but
It's increasing because it's going up, right? The picture's going up, that's increasing,
but
okay.
over time it's increasing at like a slower rate.
Okay, so it's leveling off, in other words, in mathematical terms, isn't it concave down? So if you are increasing in concave down, that's exactly what this situation is. Perfect. Okay. All right, well, okay, we're gonna review again tomorrow because, and we might start 1-4 tomorrow too, but I got a couple more things I wanna look at. So we'll review a little bit tomorrow, and our quiz will be the next time after all that.